Thank you all for joining us. My name is Lindsay Bezic. I am at home in a safe space, so I'm going to remove my mask at this time. And I am a graduate student in mechanical engineering, and I work in the Dreams Lab. And we have here also Amanda Way, who is also a Dreams Lab member. We actually come from slightly different backgrounds. I started at Virginia Tech as a freshman, intending to do the Accelerated Master's program. And then I found myself in the PhD program. And Amanda, if you want to introduce yourself and say a little bit about your background.
Yeah, thank you, Lindsay. Hi, my name is Amanda. I'm at home in a safe space, so I'm also going to take my mask off. But as Lindsay said, I'm also a graduate student at Virginia Tech, and I'm her lab mate in the Dreams Lab. I actually did my undergrad out of state in Florida because I'm from Florida, and I came here for grad school. So.
All right. Well, we have a great tour lined up. I'm a little biased because I am the one giving the tour, but I will show that video right now. It's about 20 minutes, so enjoy and feel free to think about different questions, and afterwards we will answer as many things that you ask. Thanks. Hi, my name is Lindsay Bezic. I'm in my 4th year going for a PhD in mechanical engineering, and I'd like to welcome you to the Dreams Lab. So in the Dreams Lab, we do not study sleep. It's actually an acronym for Design, Research, and Education for Additive Manufacturing Systems. So additive manufacturing is a process to build parts in a layer-by-layer fashion. 3D printing is actually a subset of additive manufacturing. And so on the tour today, we're going to take you through 5 different types of additive manufacturing. You've probably seen printers in schools and libraries. That's just one type that we're going to cover today. So, welcome. Our first stop on the tour is the powder room. So here we have 2 large industrial systems. So how does powder bed fusion additive manufacturing process work? Well, here we have a build plate and then another plate that is called the feed chamber. Both of these plates are operated by pistons underneath that allow them to go up and down. On the feed side, we stick all of our powder material that we're going to be building with. When we're ready to build, we're going to push that feed chamber up the distance of 1 layer, and then a roller is going to come and push that powder over on top of the build plate. Then, from up above, there is a laser that's directed by mirrors, and it's going to sinter or partially melt the powder that is directly on the build plate, depending on the cross-sectional area of your part that you want to print. So remember, it's a layer-by-layer process. So after that layer is fully sintered, then the build plate is going to lower the distance of 1 layer, and the process is going to start over again. We're going to have the roller push another layer over, and so on. After the parts are done printing, you have to depowder them or remove them from the vat of all of the powder material. The parts that he's working with actually look like this. We are coordinating with a hospital nearby in Roanoke, and they have masks that need exhalation valves. And so we're printing these parts because they're really small, so it's possible to get hundreds of them in a single build. And then they're also a custom part that we could design to their specific masks. And then they can put them on each of the ones that they need. Another advantage of additive manufacturing is the ability to print parts that move, all in one assembly, like this chainmail. So you can have reduced assembly and the moving parts. This part was actually designed by high school students. And the point of it was for armed forces to be able to have a portable quadcopter that they could stick in their backpacks. They need the quadcopter. They can just turn it over, open it up, and then you have all the electronics assembled, and then the blades are on the other side actually. So it'd be like this. And then you have a fully working quadcopter. In this section of our lab, we have the second process, binder jetting. Now, binder jetting is actually really similar to powder bed fusion. You still have the build chamber and the feed chamber with the powders. But now instead of using a laser, you have a print head that is depositing liquid binder or glue directly onto the powder. And that's what fuses those powder particles together. Now, if you're thinking, compared to a laser melting the powder versus this, where we have the powder particles just being glued, it's probably not going to be as strong. And that's why binder jetting requires a post-processing method, where after we take those parts out of this printer, they're called green parts, we stick them in an oven. And in the oven, the binder is melted away, and then the part is able to fuse together. The main binder jetting research has been with copper. Another big area of research in binder jetting is with printing pharmaceuticals. So if we take a look at some of these pills here that one of our mastering students, Susan, created, she was trying to tailor the drug release. And so when you're 3D printing a pill, you want the medicine, but you also want to make sure that it dissolves at the right time. It can't be too soon, and it can't be too slow. But we could even take this a step further and make customized geometries. Can you picture a 3-year-old taking medicine that is in the shape of a dinosaur? I think as a 3-year-old, I would have really preferred taking medicine if it was like that. And so that could be the future of pharmaceuticals through this research. A part like this, made out of metal, would not be able to be created any other way, just because of the complex lattice structure in there. You would not be able to chip away anything in the center of this part. The way that we create this is by casting. We use binder jetting to create the inverse of this shape. Then we take it over to the foundry, and they pour the molten metal around that inverse shape. And the binder, again, melts away. All that, the sand particles also fall away, and then you're left with something like this. We can take that even a step further with these larger parts and embed, here we have steel wires. And so this part is even stronger than the capabilities of just the single metal material. This is our extrusion space. So extrusion is probably the process that you're most familiar with. It's like a glorified hot glue gun. You have a filament of material that is fed through a nozzle that is heated. And once it's heated, it partially melts, and that's how you can create your lines and shapes. We have both industrial size machines that do the same exact thing as the smaller machines that you're probably most familiar with, which some of them are right over here. Some of our research in extrusion involves coming up with new materials. High temperature materials is one of our main focuses with that, but we also work a little bit in robotics. One of the most recent senior design teams built this robotic arm, and in building the robotic arm, they put the extruder tip at the very edge of it. And so now, instead of only having the ability to print in the Cartesian coordinate system, only straight across with the build plate moving up and down, you now gain additional degrees of freedom. So now, the robotic arm can turn on its side, and you can print parts like this, where for each one of these claw edges, the robot moved to the side when it was printing. And this gives the part a lot more strength. Some of the research that our graduate student Joseph has been doing in this space was with what we call topology optimization. And that is trying to create the best, most efficient roads or extrusion paths in order to create the strongest parts. This research has come a long way. One of the very first bases that was created was this one here. And as you can see, this would not be a very functional base. Like, there are a lot of different holes in the sides. And that's just because the process parameters weren't tuned enough to be able to start and stop the material at the right time. But over time, our research has led to the ability to create the larger structures with no holes on the sides. In another space, we actually have an even bigger robotic arm that's able to print things like this. process. This is actually most similar to how your 2D printer works, but instead of putting ink on a piece of paper, it's jetting a photopolymer onto a build plate. So photopolymer, photo meaning light, polymer meaning plastic. We are essentially building plastics out of light. And so you can see as the printhead moves across the plate, it is depositing the material. In this case, it is tensile testing dog bones specimens. And then you have a UV light that's on the entire time, that whatever droplets are jetted onto the build plate are being simultaneously cured. One advantage that this printer has is the ability to do multi-colors and multi-materials. An example here is a wheel where you want a more rubbery, flexible material on the outside, but a more rigid material where the axle is on the inside. So this was printed all as one piece. Now, besides having just this black material and this white material being placed adjacent to each other, we can also combine those droplets. When you're controlling the material at a droplet level, then when they're side by side, you can actually make different grayscales between these two materials. And the material properties that they'll have are in between this most flexible and this most rigid. An example we have here is taking those grayscales, and this is an old lab picture, and in the most brightest sections of this picture we use the white material and it's rigid. Wherever it's the darkest blacks, it's the black material and it's super flexible, and you have that material gradient in between. And so some of our research is in the design aspect, trying to come up with different either lattice structures or just different configurations of these materials controlled at that droplet level to be able to come up with desired properties. Some of our other research has been with the medical field and taking CT scans of either skulls, or in my case, in my research, it would be with hearts, and turning them into printable models. So I was collaborating with cardiologists at the hospital in Roanoke. They were taking CT scans of their patients, and we were turning them into printable models that instead of the screen that the doctor would look at to try to plan the surgery, they could actually have the heart in their hand and use their tools and see, can I get my instrument into the veins or the arteries that need to happen? So this is a great pre-surgical planning tool, as well as a medical student education training model. But we wanted to take this a step further. Utilizing the flexible material capability that this printer has, can we make these hearts have tissue mimicking materials? And so that was a big aspect of some of the research I was doing. The material jetting process is also great for our cybersecurity research. And so this is a mechanical engineering lab, but as you've seen, we've worked in the biomedical field. We also work with computer scientists. And so in the field of cybersecurity, we're wondering is what you intend to print what is actually printing? And this could be a big issue, for example, in the Navy, where they might put a 3D printer on their ship, and if a part breaks, then they're able to download the digital file and print it. But what if someone with malicious intent were to hack those files that you're sending to the printer? If that is a bolt and they put an internal void in the part, then when it prints, you might not even notice it, and that could be a potential failure mode and be very harmful. Here's two examples of parts that look identical, but when you hold them up to the light, you can see there is an internal void in this part here. And so this is just one example of how you could hack the STL file and change what was intending to be printed. And so we have a couple researchers using all kinds of different methods to see if they can detect these vulnerabilities and also plan for how to avoid them. Finally, another use of the material jetting process is with embedding parts. So we have this wing as an example. It has that flexible material in the hinge, And it also has embedded strain gauges and a variety of different sensors. And the reason for that is that when you bend the wing, then you can measure how much strain is on that wing. So this was printed on this machine, and we had to pause it in the middle of the build in order to overlay these electronic components and then continue the build to finish it. So again, with the material jetting process, we are patterning the material and we have a bulk light source. Now the other process in this room is called vat photopolymerization, and it is the opposite of that. Now we have bulk material and patterned light. So what does that really mean? Well, let's take a look at this custom-built machine that our researcher Vishwanath made. In this receptacle is where we would have the vat of liquid material. And then we would have a build plate, which isn't attached at the moment, but it's about the size of that slide there. The build plate is going to dip into this vat of resin. And then this is a hacked projector, and we stuck a UV light in it. And so now you can use the UV light to project whatever pattern you want of that cross-sectional area. And so whatever the light hits instantly cures. So then that build plate can again move further down into the resin, and then you create your parts like this one in that layer by layer fashion. The reason Vishwanath made this machine was his research was in trying to make larger parts at high resolution. And so instead of projecting just a single image, he was projecting a movie while moving the UV light. And so now, instead of scanning just this small area, you're scanning a much larger area. Now actually, on the flip side, we have research with that photopolymerization doing even much smaller parts. As an example here, we have a couple lattices and even a tiny hokey bird there. The reason for doing this research was the grad student Nick was collaborating with chemists and creating lattices that cells could grow on. So he was creating these small lattices of different materials and of different geometries and taking it over to work with the chemist to drizzle cells on them and to see how many of them stuck. Other research in vat photopolymerization is with material scientists. So a lot of them are synthesizing new materials, and we're trying to see if we can print them. Our final stop on the tour is this machine here. We call it the Dream Machine. I was actually part of the senior design team who built this. Now you've seen material jetting, extrusion, binder jetting all over the lab. Each of these processes can only handle certain types of materials, and each process has different advantages. So we wanted to take all of the processes and put them together so that we could create multifunctional parts in new ways. And so we see that here with our giant print head. This front system is material jetting. We have the spot to put in multiple extrusion nozzles. We have binder jetting by taking an HP printer print head, hacking that, and turning it into something that can jet binder. And then on the very back, we strapped a UV projector. So we have it all. We have the beds that can handle either liquids or powders. And so going back to looking at this wing, the disadvantage of printing this and pausing it in the middle of the build is that the printer doesn't know that we're adding all these external parts. But with the full control that this system offers, now all of a sudden we can start printing with either extrusion or with the vat photopolymerization, for example. And then we can just change tools in the middle of it. So one great example of that is using paste extrusion with a silver ink. And so if you put that in the middle of that photopolymerization part, all of a sudden you can create a circuit. You basically printed an embedded wire. And so we have a lot of applications with that. And that's where we also collaborate with some of the electrical engineers to be able to create different applications for multifunctional use. Thank you so much for coming on this tour. I wish you guys could have been here in person. So maybe if you come to Virginia Tech and you're in engineering, we will possibly cross paths and you'll get to have a full experience of our Dreams Lab. Before I go, I would love to tell a little bit more about my story of how I got to be this fourth year PhD student now, which seems unbelievable, as I started as a freshman at Virginia Tech. So I actually double majored in mechanical engineering and vocal performance. I didn't really know much about mechanical engineering coming in. I just knew that in high school I really enjoyed math and science. I liked hands-on things, and I loved singing and theater and all the arts. And so mechanical engineering just seemed like the right fit. Originally I was going to plan to possibly do something that mixes them, like acoustics, but I really fell in love with the creativity that additive manufacturing and 3D printing provides through either the design elements or the materials testing, or just the ability to collaborate with all the other engineering disciplines all in one. And so whatever school you go to, whatever major you choose, you're going to have plenty of opportunities out there, but now you're in control of seeking them out. One of the easiest ways to get involved, and I highly recommend it, is to get involved with undergraduate research. I started as a sophomore doing undergraduate research in the summer, and some of those small projects that I did in the Dreams Lab actually motivated what I am doing now in my PhD. Don't be afraid to reach out to professors, because if you see one of the professors doing something really cool in their lab, you might be able to volunteer with them and at least get to know what they're doing and to learn more about all the different things going on at the university. Thank you very much for joining me today, and I hope to see you soon at Virginia Tech. All right, well, now the floor is open for questions.
I guess to begin with, I actually have a question. So I know one way that you told freshmen that they can get involved is to get involved through undergraduate research. So what other pieces of advice would you have for incoming freshmen, and what would you have potentially done differently, or what do you appreciate that you have done?
Well, for me personally, at Virginia Tech especially, we have the Gobbler Fest at the very beginning, where there are just all the clubs laid out all over the drill field, hundreds of them at different booths. And so I came in wanting to do it all. Like I said, I had double majored in music and engineering. I was taking millions of credit hours, and I was crazy. But I learned really quickly you cannot do it all. But you can still get involved in a lot of different things. And so being able to go to those different booths and see the different clubs and organizations, and then pick maybe 3 of them to attend their opening meetings and see if there's something that you want to stay involved in for a longer period of time. I think that really helped me, and it's a way that each person can find their unique interests or maybe something new that they've never tried before.
I guess to kind of add on to that, I would say as a freshman, it's really important to go out and seek new opportunities. Like you're in a new place, a new town, probably making new friends. It's all really exciting, and it's a really good time for personal growth. So don't be afraid to, go on a limb, make new friends, talk to different people, and seek out opportunities like internships, research, and stuff like that.
Okay, that's awesome to hear about advice that you have for incoming freshmen. And what are some challenges that you may have faced in your freshman year that people can have, steps forward in tackling, or even specific to COVID now that we're entering back into having face-to-face instruction and stuff? What pieces of advice do you have in taking advantage of any opportunities that you have with in-person meetings and opportunities?
Well, to go off what Amanda had said, my challenge was actually making new friends. When I came, I did not know a single person, and I'm an introvert.
And so I really didn't want to make friends, even though I knew I needed to. And so the dorm that I was living in highly encouraged having an open door policy. And at first I didn't really like it because I liked having my own space and the quiet to study. But being forced to do that and go to the lounge and just hang out and do work there got the exposure to other people and seeing different people with different interests, joining the hall for different outings to get food or to play different sports, I think was really impactful, even though I didn't see it at the time. And some of them became friends for multiple years because of that.
I guess to answer that question, I would say, especially with, I guess everyone's working in like a virtual environment now and you're taking classes, it can be really easy to fall behind just because there's more of a disconnect between you and like the rest of the class. And therefore, you may feel like there's less of a compelling reason to keep up. But it is important to keep up just because staying on top of things is always good. But if you fall behind, it can get really stressful really quickly. So my recommendation is to try to set up a routine and make sure you're holding yourself accountable to things and make sure to take breaks along the way. But I know, especially as a freshman, I guess coming to a new place, you want to go out, meet people, do things. So it can be really disappointing if you end up having to take a lot of classes online and work from home a lot of times. But the world is moving more towards like a virtual environment. So think of this as like an opportunity to practice your skills of self-management and also just getting used to using technologies to communicate and work with other people.
Yeah, and there's definitely a big shift going from high school to college, where high school is like you have a set schedule of like 8 to 3 or whatever time period. You are in school, you are doing school. And then you have a short interval of doing homework or doing extracurriculars. And it's very structured. Whereas at college, like you have complete flexibility. If you want only classes after 3 p.m., you can make that happen. But you also have to figure out that work-life balance in a new way.
Okay, yeah, that's really, really awesome advice to hear from both of you. Thank you everyone so much for coming. And thank you again to our panelists for giving us such an awesome performance.
Thank you as well.
Yes, thank you for having us.